Okay, moving on to problem 2. This is the one about the TJ Marching Band. More or less I've got it up here. They go from the mud, where they're moving at half normal speed, to dry ground, where they're moving full speed. And I gave you, right, these are the speeds. 2 is the dry ground, 1 is the mud. And what we gave you, or what I gave you, was this angle here, which I said was 65 degrees. Okay, so the trick is, I think you probably realize this now, that this is actually a refraction problem. So they're marching along and they go from basically being in a slow medium to being in a faster medium. What happens? And so if you want to think it through a little, imagine, they're marching along and then the first wave front hits, or, one wave front hits the boundary. Say it's halfway through. Well, these guys on the other side have been going faster, right? So they've sort of moved ahead and turned the whole band this way. So you can think of it as working like this, okay? And then the band ends up going that way, and here's like the next one through. Think it through like that, and I hope you can see it working. This is one of those things where I try to sort of get you to see the, I don't know, the beauty of nature, or how patterns recur, and all that crap they teach you in math and science. Anyway, well, it's true, but I mean, you've heard of it a lot. Okay, so anyway, the first question is pretty simple. The first question is they start off 5 meters from what you might think of as a wave to a wave. So you might think of each each line of marchers as being a wave crest, and in that case they were 5 meters apart, which, I don't know, is that normal for a marching band? It seems awfully long to me, but, well, I mean, I wrote the problem, I guess I can't complain, right? So, this one's not very hard, because this is just an application of B equals F lambda. So the frequency you can think of is the number, it's the number of waves per second. In this case, it's the number of lines of the band that pass a given point per second, or within some unit of time. Okay, so if we take lambda as being 5 meters, frequency is whatever, and then the velocity, or the speed of the wave, changes. In fact, the speed of the wave doubles as you go from the mud to dry ground. So if the speed of the wave doubles, and this stays the same, then lambda must also double. So the wavelength out here is going to be twice as long as the wavelength we had back here, and that's going to be 10 meters. So that's your answer for part A. Part B says how, oh, right, which direction they turn and by what angle. So I hope I've sort of showed you here that they're going to turn to their left, right? Because what they do is they go, they're going sort of straight to the right on this page I've drawn, and then they turn towards up. And so if you think of them moving this way, obviously they're turning left from their point of view. It's a left-hand turn. So by how much, of course, is the next question. And the trick there, and this is something I've told my students time and time again, I'll tell the rest of you, one of the things we will try to burn you on, I can almost guarantee it, is what is the definition of angle of incidence and angle of refraction. This 65 degrees I gave you here, this is not the angle of incidence. The angle of incidence here is this. Okay? It's a line from the direction of travel to a normal line to the surface. Okay? This blue dotted line I drew here, or dashed line I drew here, this is supposed to be a right angle symbol. It sucks, I know. Whatever. So, I mean, it's horrible, I know, whatever. So this is, you measure from the direction of travel to the normal line, or alternatively, you can measure from a wave front to the normal line. So we could say, I'm not to the normal line, sorry, wave front to the surface. So we could say, we extend this wave front down this way, and then we say, oh, this angle here is theta 1 as well. I'm going to stick with this one, and since this is a right angle in here, and the complement of our angle of incidence is 65 degrees, then obviously theta 1 equals 25 degrees. And so the way you do this is, frankly, this is just a case where sine theta 1 over sine theta 2 equals V1 over V2. Okay? So since V1 is 1/2 of V2, then that's just going to be 1/2. And so you find the sine of theta 1 and the sine of theta 2. and then you find, well, so you find the sine of theta 1, wait a minute. Yeah, right, double it. So sine theta 2 equals 2 times sine of 25 degrees, which is theta 1. And I want to say, I don't remember exactly what that comes out to be, but I want to say theta 2 is around, geez, what is it, like 57, I think? Approximately 57 degrees. Don't quote me on that, like you ever would, but I'm not 100% sure of that. But I think that's about right. I don't want to check my notes right now because I don't care enough. So that's around 57 degrees. And so then the question was, by how much have they turned? So you do a little geometry and you find that basically if you compare this horizontal line here, this was their original path, this blue dashed line, or now solid line going this way was their original path, and this is their new path. You find that it's like a 32 degree, maybe 32.2 degree turn, so the correct answer is like 32 degrees left. Again, that's if I remember correctly. If I'm wrong, don't invest your money based on what I say. Okay, so question C then is, what happens if this angle here is 45 degrees instead of 65? What happens? So in that case, if this is 45 degrees, then theta 1, which is the complement of 45 degrees, is also 45 degrees. So now theta 1 equals 45 degrees, and sine theta 1 equals 0.707, or square root of 2 over 2, and then the sine of theta 2 is going to equal just the square root of 2, which quite clearly is greater than 1, which means theta 2 equals, this is where the universe says WTF. No, not really. What the universe actually says is total internal reflection. So, how far you want to go in sort of talking about how the band deals with this is up to you. I didn't really intend anyone to go further than realizing, okay, it's total internal reflection, so this isn't going to work. What I could try to say here is, in the case of total internal reflection, what happens is, so here's like a wave front coming in, and then this wave front is hit, and this part here has reflected. So this is the part that would be down there, and then this bit would be there, and it's reflected like that, and it actually goes further and goes through this other one. So, each individual band member would basically come out and then sort of do this loop and go back in. And because basically, for a given band member, so here's your, what the hell is that? Sounds like someone's torturing a cat in the hallway. Not really, and I certainly hope not. What happens for a given band member is they come out, their right foot then gets on the dry ground, and their left foot is still in the mud. And so, in this model, what you'd say is, well, the right foot then is going to move a lot faster than the left foot. And obviously this doesn't work for people walking, but think of it like a Segway or something. And this curves around like that, and this just curves sort of gently in there, and so the band member ends up walking up this way. But, then you have this thing where, like, the people who were on your left are then on your right, and the people who were on your right then on your left, and it's all weird and crazy. So I don't really expect you to sort of analyze it down to that level. I'm just, having fun, goofing around. What happens if the band tries to total internal reflect? Who knows? It's crazy. Okay, anyway, but that's all you really need to worry about for problem 2.